Hi students, in this video we're going to look at rectangular hyperbolas. So our learning goals for this video. So after watching this video you should be able to recall the equation for a rectangular hyperbola, sketch and label the key features of a hyperbola including the asymptotes, that's a new word, we'll define that one as well in this lesson, understand how the dilation affects the shape of a parabola, and then apply rectangular hyperbolas to problems involving inverse proportion. Right, so a few things we have to recall how to do. We have to learn how to remember how to substitute into a formula. That will help us get some points for our hyperbola. Another thing to recall is that numbers cannot be divided by 0. Right, they are undefined if we try to divide by 0. Right. Alright, so a rectangular hyperbola is a graph with the equation y equals a over x, where a is the dilation and a cannot equal 0. Right? Now that makes sense. If a equals 0, then we get y equals 0 over x, which is just the line y equals 0. So that's not a hyperbola. Y equals 0 is just a line. So a cannot equal 0. Notice here, students, we've got two branches. So we've got one branch up here and a second branch on the bottom here in that bottom left quadrant. Right, now students, notice that the two branches of our hyperbola never cross the lines x equals 0 or the line y equals 0. So these two blue lines here basically trap and enclose our hyperbola, and our hyperbola can't cross those lines. They'll get very, very close to those lines, as you can see. These graphs, these curves are getting very close to our hyperbolas, but they're never going to touch them. These blue lines are called asymptotes. So asymptotes mean that our curve gets very, very close to that line without actually touching it as you go further and further along. Okay? Now these asymptotes can be found using the equation of our graph y equals 1 over x. So we can say if y equals 0, then we have 0 equals 1 over x. Multiplying by both sides by x, we end up with 0 equals 1. Now that's not true. That can't happen. 0 can't equal 1. So therefore, y cannot equal 0. By the same token, if x equals 0, we have y equals 1 over 0. We can't divide by 0. So therefore, x also cannot equal 0. So that's where the asymptotes come from. Saying that if these things do happen, if y does equal 0, that doesn't work, and if x equals 0, that doesn't work either, because you can't divide by 0, and for y, the y value can't be 0 because we can't have this fraction, 1 over x, that fraction can't be 0. You can't have 1 of something and divide it into pieces so that everyone gets 0. That's just not possible. Alright, so when the dilation is greater than 1, so a is greater than 1, the graph moves further away from the asymptotes. So that's what's happening with this purple line here at the end. It's moving further away from our blue asymptote lines compared to the red one, which is just 1 over x. So that purple one has a dilation of 2. It's further away. It's been stretched away from those asymptote lines. Now, if the dilation is between 0 and 1, like this black line, that one's got a dilation of 1/4. It's been compressed. It's being compressed into the center of these asymptotes. It's getting closer and closer to those asymptotes by making that dilation smaller between 0 and 1. Now, when the dilation is negative, our hyperbola flips across the asymptotes. So we've got 1 over x here in the red. When it becomes negative 1 over x, the branches flip sides. So instead of being in quadrants 1 up here and quadrant 3 down here, they've now flipped to be in quadrant 2 and flipped to be in quadrant 4. Okay. So when the dilation is negative, those branches flip across the asymptote. Now when we're sketching a hyperbola, the key steps are drawing the asymptotes, which in this situation that we're looking at now, they'll just be 0, 0. We then substitute in the points x equals 1 and x equals -1 to locate some points on the parabola that we can use to draw our branches, and then we draw the branches between those points, between the asymptotes and through the points we found in that second step. Alright, so now let's sketch the following hyperbola. So our first one is just the simple one, y equals 1 over x. So first of all, our asymptotes, those are just 0, 0. So x can't equal 0 and y cannot equal 0. So we'll draw those in, x equals 0 and y equals 0. And the branches of our hyperbola have to fit in between those asymptotes. Now, first of all, let's let x equal 1. So that means y equals 1 over 1, which equals 1. So my first point on my hyperbola is 1, 1, which is right here. For the second point of my hyperbola, we'll substitute in x equals -1. So y equals 1 over -1, which equals -1. So the second point there is -1, -1, which is here. And then we can draw the hyperbola by saying it's going in between our asymptotes and through the point 1, 1 and -1 and -1. Not the neatest in the world, but close enough. Right, there's the first one. Now I'm doing the second one. We've got the same asymptotes, okay, 0, 0 for our standard hyperbola. And so let's sub in those points. If x equals 1, then y equals -2 over 1, which equals -2. So therefore our point is 1, -2. Then if x equals -2, then y equals, if x equals -1, then y equals -2 over -1, which equals +2. So our second point is -1, +2. Alright, plotting those points. 1, -2 is down here. And then -1, 2 is up here. So our hyperbolas have flipped, and we could see that because we've got a negative dilation. So it should be in those opposite two quadrants, not top right, bottom left, but top left, bottom right. And then we can draw our hyperbola with those points. Y equals -2 over x. And that's how we go about drawing our rectangular hyperbolas. Alright, so one application of rectangular hyperbolas is graphing situations that involve inverse proportion. Now, inverse proportion is just when one value increases, the other decreases according to some sort of constant. So that is, y is proportional to, that's what this little fish looking symbol means. It means proportional to, and that's 1 over x. So that's inversely proportional, right? because y is proportional to 1 over x. It's proportional to the inverse of x. Now turning that into an equation, we can say y equals some constant k times 1 over x, which simplified, k times 1 is just k over x. So we get left with this equation, y equals k over x, which looks a lot like our rectangular hyperbola. So any situation that involves inverse proportion can be modeled using a rectangular hyperbola like this one here. Alright, so let's do a quick example. So two landscapers are able to lay turf for a new yard in 1 hour. assuming the time taken to do the job is inversely proportional to the number of people doing the job, determine the equation for the time taken to do the job in terms of the number of people. So we're told that it's inversely proportional. So the time taken to do the job is inversely proportional to the number of people doing the job. Let's call that n. I'm turning that into an equation. T equals k over n. And then we can sub in our values. So sub in t equals 1 hour and n equals 2. So we can say 1 equals k over 2. So therefore k equals 2. So the equation is the time taken for the job equals 2 divided by the number of people doing the job. Right, determine how long it would take for 3 people to do the job. So that means n equals 3. So t equals 2 over 3. Now that's in hours. So that's t equals 40 minutes, 2/3 of an hour. Determine how many workers it would take to do the job in 24 minutes. Alright, so for this one, so time equals 24 minutes out of 60 minutes in an hour. So as a fraction, that is 2/5. So therefore, 2/5 equals 2 over n. Looking at this, 2's are the same on top, so the denominators must be the same too. So n equals 5. It would take 5 people to do the job in 24 minutes. Alright, so after watching this video, students, you should be able to recall the equation of a rectangular hyperbola, sketch and label the key features of the rectangular hyperbola, including the asymptotes, understand how dilation affects the shape of our hyperbola by moving it away from the asymptotes or towards, or by flipping it over, and then apply rectangular hyperbolas to solve problems involving inverse proportion.